So we are closing with our travel through design variable, design flow, and design hydrograph estimation. So this has been the first part of our course. You remember that we start from the practical problem and then go back to the theory, and this has been an example where indeed we started from the objective of estimating the design hydrograph, and then we went back to the models and to the underlying theory. And this is something that I consider now closed, and I just wanted to conclude with some consideration, but besides that, I just wanted to tell you that I am looking for a compilation of useful YouTube files for finding some examples of the phenomena that we are looking for and we are studying. And I didn't complete, but I just wanted to show you some example. And the purpose of doing that is that I would like to encourage you to also look for these materials. I'm not sure. Let's see, maybe that I spoke too early, because maybe the connection is not so easy. But let me check. Otherwise, we can use alternative means. And basically, the purpose of what I'm saying is try to make an effort when you study these concepts and these models to look at the web to see if you can see some, you can get an idea of how these phenomena evolve and what are the implications. And this is part of forming your experience on these processes. And while I wait for getting the connection, unfortunately, it should work because it's, the signal is quite strong, but it's probably too busy. Okay, I'm getting the connection through the USB pen. Okay, perfect. Should work, let me see. So this, for instance, is an example of a debris flow which recently occurred in Italy. And let me see if the connection with the USB pen works, otherwise we can make this tomorrow. Okay, I think it's quite slow, so let me go back to the next topic. Let's see, maybe tomorrow I can show you these YouTube files. And I just wanted also to take the opportunity to discuss and to show you some relaxing, to take some relax before introducing the next topic, but I think that it's definitely too slow. Okay, so let me now introduce the next topic then. And the next topic, let me start from the technical question or the solution that we need to inspect. The next topic that I would like to talk with you is estimation of water resources availability. I still don't have the lectures ready, but I am at a good stage, so I will, I think by the mid of next week, I should be able to present on my website. You can check once in a while a page introducing this topic. And this is extremely relevant. It is extremely relevant because it is the support for any operation of water resources management. In order to devise a strategy for water resources management, you have to get an idea of water resources availability. What is the amount of water resources that you can dispose of? And it looks like a very simple question. You may think that it's an obvious question, but indeed, estimating how much water is available, it's a very challenging task. And the task is challenging because, as I said, we have a limited knowledge and only a limited measurements of hydrological processes. So even if we live close to a river, it's difficult to get a quantitative idea of the amount of water that we can dispose of. And this is particularly concerning, of course, when the amount of water is limited. And therefore, this is indeed a relevant question. And it becomes even more complicated when your primary water supply source is groundwater. Because if it is difficult to estimate the volumes of water that can be withdrawn from a river, it's, you can understand, even more difficult to understand what is the sustainable volume of water that you can extract from an aquifer. This is extremely challenging. And, but even when you deal with rivers, it's extremely challenging to get an estimate of water resources availability. Because you need a lot of measurement. The problem cannot be resolved by measuring the river discharge for 1 year. You need a lot of measurements because hydrological variables and water resources availability are extremely variable, extremely varying in time and space, but also in time. Even if we fix the location, the variability in time is very pronounced. So we need a lot of measurements, and in many cases we don't have any measurement available, which means that we need to devise strategies for estimating water resources availability without, the support of observations. The problem is made more complicated today because of the threats given by climate change. Basically, climate change is expected to induce an additional variability in water resources availability, and it's a type of variability that we suspect that cannot be estimated by looking at the past. We are not really sure of this, but there is the concern that climate change is inducing changes that were never experienced before. This is not proved, this is a concern, but still it's a relevant concern. And if these changes were not experienced in the past, it means that observations cannot help us in predicting these changes. There is to say that climate change is not necessarily dangerous, meaning that there is a very skeptical say that says that climate change will bring wet region wetter and dry region drier. This is excessively skeptical. Indeed, climate change is inducing a change in water resources availability, but not necessarily the change is bringing the situation to worsen. It's not necessarily like that. And but still it's a complicated process to gain an interpretation, because, and even if it is naturally induced climate change, even if it was natural, it would be a concern anyway. It would be a concern because, our need for water today is higher and higher than in the past. And the reason is that there is an increasing number of people that need safe access to water. And also our individual requirements for water are increasing. So it is a fact, and it's proved that the water requirements of humanity are increasing. And therefore, even if these changes in climate were natural, and even if they cannot be really easily predicted, of course there is the concern that the modern society is more vulnerable because it has higher and higher requirements in terms of water with respect to the past. So climate change makes this problem even complicated, because as I said, the essence from the technical point of view is that some people say that the past is not representative of the future, and therefore observations don't help us to resolve the problem. And also there are, today, there is an increasing evolution of society which makes devising strategies more complicated than in the past. And I want to bring you an example, which is the virtual water trade. Basically, we are used to consider that water cannot be easily transferred. So if you have a water deficit in a region of the world, and you have plenty of water in other regions, for instance, look at the north of Europe. North of Europe, they have plenty of water. And if you look at the south of Europe, you have instead a condition of water scarcity. We always assume that we cannot transfer water from the north of Europe to the south of Europe because it's too expensive, it's impossible. So this is still true, but today there is an added opportunity to transfer water, which is not to transfer water itself, but to transfer goods that require water to be produced. So, for instance, if we transfer food, or if we transfer meat, it's a way of transferring water, because instead of bringing water to the south of Europe to cultivate the lands, it may be cheaper and easier to bring to the south of Europe the meat or the food. And this is called virtual water trade. And this is very relevant because the virtual water content of food and meat is indeed very huge. And I don't remember let me see, I don't remember the numbers well, but it's impressive how much water is required to produce 1 kilogram of meat. And if I get the connection, there is a website that explains this, which is very helpful, and let's see if I can get the connection, I will tell you. So basically, exporting meat instead of exporting water means that it's equivalent to exporting a lot of water, but it's easier and cheaper. And therefore, the virtual water trade is today an area of research that is increasingly inspected and analyzed by researchers because it's a possible solution. The problem is the economical implication, because of course the virtual water trade implies a corresponding socio-economical dynamics. So basically we should avoid the situation where the countries which are water rich take the opportunity to gain money at the expenses of poor countries for exporting the virtual water. And so the socio-economical implication should be adequately considered with an overall coordination, which is not easy. So, how can the problem be solved? Estimation of water resources availability. We need observations. This is something that we have to have in mind and to make clear. We absolutely need observations. Even if climate change is posing the threat that the past is not representative of the future, observations are still and nevertheless the starting point. And this is a concept that I really would like to highlight, because you know, even if the future will be different from the past, we need to start from a knowledge of the system in the past and in the current situation. And then we can make prediction on how the system will change. But for gaining a knowledge of the past and present status, we strictly need observation and monitoring. And I think this is a danger that is related to the concept of climate change. The danger is that people get convinced that monitoring, observing, and studying the current state of the system, the Earth system, is not useful. The danger is that people will think that the future will be abruptly different from the past, and then they will neglect the value of experience. This is a real danger. I mean, we have to understand the change, so we have to understand the derivative if you want, but still we need the initial condition. And the initial condition is given by the present status and the past situation. And without defining the initial condition, we cannot be able to make any prediction on the future. So I understand if people say that the initial condition is not sufficient. I understand if people say that the data cannot tell us by themselves alone how the future will be. This is fine, but still we need the data. And for instance, another say that we usually listen to in the current days is that probability analysis and retro period is not reliable in front of climate change because the concept of retro period is something that is related to the study of the past, and people say this concept is no more technically useful today. And this is another wrong, this is another misunderstanding. Still, probability analysis, still the concept of retro period allows us to gain the knowledge of the past and the present situation, allows us to fix the initial condition. They are still important and necessary. Then we can understand if we can understand the statements that they are not probably enough in order to gain useful prediction for the future. But still they are necessary. So basically, from a technical point of view, we need data. So in order to find a solution to this problem, estimation of water resources availability, I will start my discussion by teaching to you how to estimate water resources availability under the assumption that we have data. And then, after that, we can turn to the situation where we don't have data, and we can turn to the climate change effects. So how to estimate the climate change effects, how to analyze, if you want, the human impact on the current and past status of the system. But the first thing is data. So let's start now from the assumption that we have data, and let's look at the classical hydrology, how water resources availability is estimated in the presence of data. And let me start with the analysis of surface water resources. So the question is, how can we quantify surface water resources availability? By using data. And then we will turn to groundwater resources availability, which is much more complicated. But now let's stick on a very simple and very classical question of hydrology, because this is the necessary starting point, and then we will make things more and more complicated. So again, what is the question is how to estimate surface water resources availability, typically by referring to a river cross-section, by using data. So our assumption implies that we have a time series of observations on river flows, and we want to quantify water resources availability. Remember that a time series is, in general, a collection of observations depending on time. So when we speak about a time series, it is intuitive. A time series is a collection of observations along time. And when talking about water resources availability, we introduce the concept of time series. And the reason is that we need a long record. For studying floods, we still need a lot of data, but it may be enough that we have flood data. So it may be enough that we have the annual maxima, for instance. So the observation period still needs to be long, but we don't need, for studying floods, a very long hydrograph. For studying water resources availability, the observation period still needs to be long, but we need all the data, not only the flood data. We need also, and especially, the drought data. We need everything. I mean everything, not only the droughts, because one typical solution for increasing water resources availability is building reservoirs, dams. And therefore, to design a dam, you also need the flood data. You need the whole hydrograph. So in this case, we need the whole hydrograph. But not just the flood hydrograph. We are moving to a different problem. We need a long hydrograph encompassing the whole year and several years. So you understand that this is a more difficult situation. And the problem that we are studying, the problem is as important as the floods. So when we speak about droughts, when we speak about water resources management, it's still a very important problem. We may think that floods are more dangerous, are more important, because floods usually hit very rapidly and kill a lot of people in a very limited time. But indeed, water scarcity is killing more and more people. But very often we don't realize it because it's a long process. It's a process that, you know, it's very long. This is the first thing that you have to keep in your mind. Floods are concentrated in time. Droughts are very long. And the heaviest droughts are very long droughts. So, I said that the question is very classical. And so let's see at what is the classical tool in hydrology to estimate water resources availability by referring to a cross-river section. And this is the first part of my lecture, of my lectures on these issues. And again, this is a very classical problem. If you look at the web, I will prepare my lectures, I will put a lot of links. Usually, water resources availability from a river is quantified through a graphical tool, which is the flow duration curve. Somebody of you already knows the concept of flow duration curve. Okay, you and you and you, who knows it already? Okay, a lot of you. Okay. So, the flow duration curve, I'm not surprised because it's a very classical concept. And basically, it's a graphical tool, but it's also analytical. I mean, it's called a graphical tool because it's typically used in graphical form. And it's useful to use it in graphical form, especially for the interaction with people, for transparency. But it has a solid analytical basis. So the flow duration curve may be depicted, but it can be treated analytically. And what is the flow duration curve? First of all, let's define it by referring to the graphical form, because it's easier. But the flow duration curve is a graph which records on the x horizontal axis, or let me start from the vertical axis, from the y-axis. On the y-axis, it refers, first of all, to a given river cross-section. And it reports on the vertical axis river flow values, river discharge. and on the horizontal axis reports the duration, so it's a time, which a given river flow is less or equal is, let me formulate it again, because it reports for in the horizontal axis, in the x-axis, reports the duration which a given river flow is equaled or inferior on average. So let me write it. For a given river flow, the flow duration curve gives the flow duration curve, let me call it FDC. The FDC gives the duration the river flow is equal let me put here the observed river flow is less or equal to the given value. I'm repeating now, because now it's correct. So, for a given river flow, the flow duration curve gives the duration, the observed river flow is less or equal to the given value. So let's suppose that we assign here a river flow Q star, and let's suppose that the duration on the horizontal axis is given in days, and let's suppose that this duration is like 150. This means that in the river, I forgot here on average, sorry. Let's suppose that the duration is 150 days. This means that, and the duration is expressed in days per year, okay? In fact, the duration can be expressed as a fraction. So let's suppose that it's expressed in days per year. And 150 days per year means that the observed river flow, on average, is less or equal than Q star for 150 days per year. So again, if I want to make this example, I fix a value of Q star, and if the duration is given in day per year, and I get a value of 150 corresponding to Q star, this means that on average, Q star, the observed river flow, is less or equal than Q star for 150 days per year. Let me say not less but greater. Sorry. I'll tell you why I put less, but let's start with greater. Less is not wrong, but let's start with greater. They are complementary, you know. Of course, greater or equal is complementary to less or equal. And let's start with greater. Okay, so basically, what is the shape that you may expect for a flow duration curve? Let's suppose that the river flow in the given cross-river section is varying between a maximum and a minimum. And the minimum could be the long-term minimum, and the maximum, the long-term maximum. So let's suppose that you have a lot of observations, and you assume that these observations are representative of the dynamics of the process. And of course, these observations have a maximum and a minimum. Okay? So let's suppose that I use the same graph. Let's suppose that we identify the maximum here, Q max, and a minimum here, Q min. So, if I start from Q max, would you expect a duration? Let's see again the definition. The flow duration curve should indicate the duration that the observed river flow is greater or equal to the given value. So if the given value is the maximum, would you expect a long duration where the observed river flow is greater or equal, or a short duration? Of course, we say a short. Perfect. So let's suppose that we start from here, and let's suppose that the duration here is, if it is in days per year, let's say 1 year. Just an hypothesis. It could be also less than 1, because it could be less than 1 day per year. But let's suppose that it's 1, okay? And then you start from here. And then let's look at the minimum. The minimum, would you expect a short or a long duration? The observed river flow is greater or equal? Of course, a long duration. So let's suppose that it's 365. And then here you get the end of this curve. And keep in mind that this is average duration. So it's number of days per year on average. It means that this is not what happens in 1 year. Should happen in many years. And then you have a decrease. From this maximum value, you have a decrease that can take place according to different behavior. And of course, it is depicted by the observations. Keep in mind that the curve could go to 0. If you have the minimum value of flow that is 0, which means an intermittent regime, the curve could go to 0. And now let me depict two possible curves. And let me ask you a question. So let's suppose that one curve is this one, and the other curve is this one. Of course, this is a not increasing curve. You cannot have an increase in this curve. It can be, in principle, could get an horizontal segment, but actually it doesn't occur, because it would mean that you have the same observation that is repeating many times, but given that the discharge is a real value, usually doesn't occur. But it can have different shapes. So what I may ask you is, in your opinion, if we have these two curves, what is the curve that refers to the larger basin? And I am asking this question because the concept that I want to stress is that the shape of the flow duration curve is strictly related to the physics of the catchment. And so I'm claiming that by looking at these two curves, you can get a guess of what is the larger basin here. And first, what is I'm not expecting a reply. I'm giving you some information to gain a reply. What is the area below this curve? And remember, this is river discharge and this is duration. So the area below this curve, it's a volume. It's a volume of water. And basically, you know, look at this curve. The white one is giving lower values of discharge for the same duration. The red one is giving higher values of discharge, which means that discharge multiplied by duration, it's a volume. The red curve corresponds to a higher flow volume. So the area below the curve is the flow volume. And it means then that the red curve refers to a higher, much higher flow volume. So I would say that it's a larger catchment. In this case, the situation is a bit strange because it would be a larger catchment with the same peak flow, but this is possible. I mean, it's possible that you have a higher flow volume, which means typically a larger catchment under the same climate, and it may happen that the peak flow is not much different, but still you have a higher volume.
Sorry, we are referring to the same river cross-section now?
No. Yeah, two river cross-sections. Sorry, because when a river cross-section is characterized by a unique flow duration curve. So when I say two flow duration curve, it means two river cross-sections. It may be also two river cross-section of the same river. For instance, if you look at the Po River in the Alps, you have a curve, a flow duration curve that is more like this, and in the downstream part, it's more like this. And also the Po River is a good example where you have the peak flow that is not changing much, but the shape of the flow volume changes, and while you move downstream. And typically, the red curve corresponds to less variability in the river flow. Here you see that, or less variability. Let's say this white curve corresponds to hydrographs that are rapidly slowing down. And so basically you get the same high flows than the red curve, but the recessing limb is steeper, and you go more rapidly to low durations.